weights are same. So, multiply by the same weight, all of them, summing them up. So, weight is pulled out. So, all observations are added up, but the weightage is given to that in terms of LS square divided by LS square plus sigma n square. Is okay? So, what is the advantage you have got here? If L is large, and this value will be much larger than this value. Individually, if we take L is equal to 1, this and this may not be satisfying the requirement that this is much larger than this. But when you observe L number of them, then this becomes much larger than this. So, this is approximately equal to 1, and so S cap is equal to summation of all this. This is the moral of the story we found in 102, if you remember, that we make observation measurements, a large number of observations. You should always take large number of observations and average them out to get the best estimate. Okay? That is what this tells you. The next question comes, what do we do if the signal is a continuous signal? Oh, I messed up myself. If the problem is that we have an R of t and an S of t and N of t, this is a continuous signal, observation continues as a function of time, and this observation is embedded with a signal which is a random signal embedded in a random process which is noise N of t, then what is the best estimate of S cap t? Given this observation from minus infinity to plus infinity, how do I find S cap t from out of this signal that is given to you? Knowing that this and this are uncorrelated. It's not necessary to use that assumption, but it simplifies to use that assumption. So, assuming that this and this are uncorrelated, both are random processes, what is the best estimate of S cap t? Same argument as before, that finally the best estimator must be such that the error is uncorrelated with the observations. So, what do we do? Best estimator will be linear estimator, where RT is passed through a linear filter and call this as the best estimator of S cap t. Right? We assume that the best estimator is a linear estimator in the case of Gaussian signals. So, assuming it to be Gaussian, the best estimator happens to be linear estimator. Linear estimator in the case of continuous signal will be a linear filter. The linear filter has an impulse response, time invariant filter, HT. So, the output of this filter will be equal to the best estimate. Now, what is the way you find out what is H has to be found? From the requirement, this should be best estimator, and the requirement will be obviously orthogonality principle. So, expected value of error into R t minus tau must be equal to 0 for all tau. Just as the case in the previously, we have so if apply this orthogonality principle, then the solution comes out to be very easy to do, but same as equivalent to Wiener or Euler-Walker equation, or as tau similar to Euler-Walker equation, but a continuous equation. That means this estimate is given by this integral equation, where the impulse response of the ideal estimator, linear estimator, will be given by solution to this equation. Agreed? Is equal to orthogonality principle. Apply here like this, you get the solution. How do we solve this equation? Very easy. Take Fourier transform on both sides. So you get SR omega is equal to SRR omega into HF omega. So the transfer function of the linear filter should be given by SR omega divided by SR omega. Right? Which is equal to S because S and R are uncorrelated, S and N are uncorrelated. So SR is nothing but SS omega, and similarly this SRR omega is equal to SS omega plus SN omega because of uncorrelation between signal and noise. They are independent processes, Gaussian process. So the filter, ideal filter in this problem, where the observation is available to you from minus infinity plus infinity, from this observation you will have to make a best estimate of what is S of t, which is embedded in a uncorrelated noise process N of t. Okay? The solution comes out to be passed through a filter which has a transfer function given by this equation. Is this realizable filter? Is it realizable or not realizable? There is no guarantee that the poles of the filter will be in the left half plane, and because this is a SS omega spectrum, spectrum is a positive value for all values of omega, and such systems will require quadrantal symmetry of the poles. So the poles in the left half plane as well as in the right half plane. So that filter will not be a realizable filter or a stable filter. So this is an unrealizable filter. But this is the filter which will give you solution to this equation when the observation is from minus infinity to plus infinity. We have been dealing with this problem of estimation in presence of observations. We put the clock backwards. We did Joule-Walker equation first and this equation next. But historically this came first and Euler-Walker came next. And the person who did this was Wiener. In around 1941 or 45 or something like that, around 40s. And in fact, this simple analysis was what transformed the whole estimation detection theory in communication, the starting point of that. And in 1940 time scale, nobody understood these equations. And it took some long time for very intelligent people to understand what Wiener has done. Today we are just doing it in the first year class or second year class, but during those days people spent hours and hours to understand how this equation has come.